In this PowerPoint, we're going to discuss significant figure conventions associated with making measurements in chemistry and doing calculations with those measurements. Ultimately, significant figures are a way of indicating how much uncertainty there is associated with a measurement or with a calculated result from that measurement. Every measurement has uncertainty associated with it, just from the practical limitations of the measuring instrument used. The convention for showing that uncertainty when you make a measurement is to always report every number that you can read directly off the measurement scale and then estimate one place past. Let me show you an example of how this works. When we use this graduated cylinder to measure volume, we can tell by comparison to the scale on the cylinder that our liquid volume is between 21 and 22 milliliters. We can tell this with certainty because each mark on this scale stands for 1 milliliter. And I can clearly tell that the meniscus for this liquid lies between the 21 milliliter and the 22 milliliter marks. Now, I wouldn't report this volume as just 21 milliliters because I can clearly tell it's over 21. And I also wouldn't report it as just 22 milliliters because I can also clearly tell that it is not quite 22 milliliters. So what I can do is estimate where between 21 and 22 this meniscus actually falls. So I make an estimate that this is about 21.6 milliliters. It's understood in a measurement that the last digit reported is uncertain. It is estimated, and it might actually be 21.5 milliliters or 21.7. This is what it means to make a measurement, to report a measurement with the correct number of significant figures. So when you look at any measurement, you can make the assumption that the last digit was estimated and there's uncertainty associated with it. Depending on the number of digits you report, this could have some pretty big implications for how reliable or precise your measurement can be considered. For example, say that you reported a length measurement as 5 centimeters in your lab notebook. The implied range of uncertainty with this one-digit measurement is between 4 and 6 centimeters. The last digit reported is assumed to be estimated. And if you only report one digit, then that's the digit that must be uncertain. That's a really large range of uncertainty for a length measurement. So next, you report it as 5.0 centimeters. Now this makes your implied range of uncertainty associated with the tenths place, that last digit reported. So now we know that 0.0 is estimated and the measurement could actually be anywhere between 4.9 or 5.1. This is definitely a better range of uncertainty. But with this ruler, we could do a better job. Each of those small divisions on the ruler stands for 0.1 centimeters. Which means that you should be able to clearly see whether the length is actually at the 4.9, the 5.0, or the 5.1 centimeter line. So the appropriate way to report the measurement with this ruler is to estimate one place past the tenths to the hundredths place. If you feel that your length hits exactly on the 5.0 line, then you would estimate one place past to 5.00 centimeters. This implies an uncertainty of plus or minus 0.01 centimeters. In other words, the length could be between 4.99 and 5.01. If you reported any fewer decimal places in a measurement using this ruler in your lab notebook, I would mark off for inappropriate significant figures. Okay, let's do a little more practice with this. With this ruler, I can read to the ones place with certainty. This means that I know exactly that the red block is greater than 4 centimeters, but less than 5. I estimate one place past and say that it is about 4.6 centimeters. It may actually be 4.5 or 4.7, but my best estimate is 4.6. Now, if I use a more precise ruler that's marked to the 10th place, I can know the length of this block with greater certainty. I can now tell that the block is between 4.5 and 4.6 centimeters, and that it's closer to the 4.6 mark. So I estimate that the block is actually 4.57 centimeters. And this is an appropriate number of significant figures to report for this ruler. Okay, finally, just a reminder that you still estimate one place past the finest mark on your ruler, even if it looks like your measurement lies exactly on the mark. Here, I can read to the ones place directly off the ruler. The block looks like it's exactly on that 3 line, or 3 centimeters. I still have to indicate that my uncertainty is not in the 3, but actually in the place after that. So I estimate one digit past by simply adding a 0 to the measurement. Now we estimate that last digit as long as we are comparing our substance to something like a ruler or a graduated cylinder where we have marked lines that we can estimate between. If our measurement is made using an instrument with a digital display, like this digital thermometer readout, we don't have any marked lines to estimate between. Instead, understand that the processor associated with this measurement device actually has incorporated that estimation step in the measurement readout for you. The last digit displayed is already estimated. That means that you don't have to add an extra place onto any of the measurements that you make for anything that comes with a digital display, like the balances that we use in our lab. Record exactly what the number is from the display, but understand that there is uncertainty associated with the last digit in that measurement. So for example, this 13.4 degrees Celsius measurement is actually 13.4 plus or minus 0.1 degrees Celsius. The uncertainty in this measurement is still there, even though you don't add that extra digit. So all measurements have uncertainty associated with them, and that uncertainty is indicated by the number of digits that are reported in the measurement. You should know that there are some numbers you'll deal with in your calculations that are considered to have no uncertainty associated with them. These are called exact numbers, and there are 2 major categories. First, any count is considered an exact number. For example, if there are 20 students in this class, I know that there are exactly 20 students. It can't be 20.6 or 20.375. It has to be 20. That's an exact number with no uncertainty associated with it. In the same way, defined quantities, like those that you find in conversion factors, are also considered exact numbers. For example, 1 foot equals exactly 12 inches by definition. If it was 11.9 inches or 12.1 inches, then it wouldn't be 1 foot. It has to be exactly 12 inches. So for dimensional analysis, when we use conversion factors, you can assume that the numbers in the conversion factors are exact. And as a result, they're not going to influence the significant figures or the uncertainty that you report in your final calculated results. So the uncertainty associated with a measurement does affect the uncertainty of any calculated result you might get from that measurement. Let me show you an example. Say I asked you to calculate the volume of the print version of your textbook. So you diligently measure the length, width, and height of the book. You report your measurements to the appropriate number of significant figures for the ruler you used. In this case, it was marked to the tenths of a centimeter, so 1 place past the decimal. So you estimate to the hundredths, or 2 places past the decimal. You then use the volume formula for a rectangular solid of length times width times height, and you plug the numbers into your calculator, and this is what you get. Can you tell what's wrong with this answer? Mathematically, it is correct. But your answer, with all of those digits reported, suggests that you know the final volume of the book with much greater certainty than you know any of the measurements that were used to calculate that volume. If your measurements indicate that you only know with certainty 2 or 3 digits, then you can't imply that you know with certainty 8 digits in your final result. Another way of saying this is that when you do a calculation with a measurement, your answer can't show greater certainty than the least certain of your measurements. You usually have to round your answer to an appropriate number of digits, and the appropriate number of digits depends on what type of mathematical operation you do in the calculation. There are 2 rules, one for addition and subtraction, and one for multiplication and division calculations. Let's start with the rule for addition and subtraction. Your answer can't have more digits to the right of the decimal point than any of the original measurements. All right, let's look at an example. We want to add together 2 volumes, 34.56 milliliters and 5.3 milliliters. The sum of these 2 numbers is 39.86 milliliters. But notice that the second measurement is actually only reported to the tenths place. Our answer has to be reported with the same uncertainty as the number that shows the least certainty, or in this case, the fewest decimal places. This means we also have to round our final answer to 1 place past that decimal. So remember your rounding rules. Look at the number just past the one that you want to keep. So if we want to keep the tenths place, we're going to round away the hundredths place. We look at the digit in the hundredths place and its value. If it is 5 or above, we can round the digit before it up by 1. So in this case, we would round our answer to 39.9 milliliters, keeping the tenths place. And this makes sense because 39.86 is much closer to 39.9 than it is to 39.8. If the number to be rounded away was actually below 5, then we would keep the digit the same in the tenths place. So say, for example, our sum was 39.84 milliliters. We would round down to 39.8 milliliters to keep the tenths place digit. Here's another example. This time I need to subtract 2 masses, 56 grams minus 3.821 grams. The difference mathematically is 52.179 grams, but the first number is reported to only the ones place. No decimals. Our answer still has to be reported with the same uncertainty as the number that shows the least certainty. In this case, that's the fewest decimal places. And we have to round our final answer to the ones place. The digit to be rounded away, the 1, in the tenths place is less than 4, so we keep the number in the ones place the same. We round our answer to 52 milliliters. Now the rule is slightly different if you're doing multiplication and division. If your calculation involves those 2 operations, you have to round your answer to the least number of significant figures in your original measurements. And this is not necessarily the same as the number of decimal places. In order to do this, you need to be able to count the number of significant figures in any reported measurement. And this means distinguishing between zeros that are considered significant or measured and those that are considered just placeholders. So before I show you an example of this calculation rule, first let's talk about how to count the number of significant figures in a number. There are 5 rules for distinguishing between a digit that's considered significant or measured and one that's considered a placeholder. The first one is that any non-zero digit is considered measured or significant. For example, in the number 534.67 milliliters, every one of those digits, and there are 5 of them, one for each place, is considered significant. So we say that we have 5 significant figures in this number, one for each place that's actually displayed there. Zeros are the tricky ones. And the next 4 rules all apply to whether or not to consider a zero in a number measured or a placeholder. So first, if the zero is found between non-zeros, so captured in between 2 non-zero digits, it's considered significant. For example, in 10.6 grams, the 0 is in between the 1 and the 6. That means all 3 of those digits, all 3 of those places are considered significant. And we say that we have 3 significant figures in this number. When we're counting significant figures, we always start with the first non-zero digit on the left, and we count all the digits that are considered measured after that. The second situation with a 0 is when the 0 is at the end of the number. When it is at the end of the number, we have to consider whether or not the number has a decimal point written explicitly into it or not. So for example, in 1.0 grams, the 0 at the end is considered measured or significant because there is a decimal point that is explicitly written in that number. The decimal point wouldn't have been placed there unless we wanted to indicate that that 0 is actually a significant part of the measurement. Otherwise, we would have just said 1 gram. So in this case, both places, the 1 and the 0, both numbers are considered significant, and we say we have 2 significant figures. If there is no decimal point explicitly written, then it's actually pretty uncertain. So for example, when we have 100 milliliters, it's not entirely clear whether those 2 zeros that are written at the end were actually measured or they're just there to tell you that the 1 is in the hundreds place. So the best rule of thumb in a scenario like this is actually to assume that any trailing zeros, meaning zeros at the end of a number that does not contain a decimal point, are considered not significant. They're considered placeholders. So that means that only the non-zero digit at the beginning is, and we say we have 1 significant figure in this number. Finally, zeros to the left of the first non-zero are never considered significant. Okay, so these are called leading zeros, and you find them in numbers that are much smaller than 1. So the zeros, and there are 3 of them here at the beginning, are simply there to show that the number is smaller than 1 and that our first non-zero measurement starts at the 1000th place. We always start counting with the first non-zero on the left. This is the best rule of thumb for not even having to think about whether those first zeros are considered significant or measured. So in this case, we start with the 2, and then we count all of the significant figures after that, all of the places. So we have 2, 3, 4. That's 3 places, 3 significant figures. So let's look at a few more examples. Remember that you always start counting significant digits with the first non-zero digit on the left. So for this first measurement, 14.5 milliliters, we're going to start with the 1 that's in the tens place in the number. And then we count all of the significant numbers that follow that to the right. In this case, it's all non-zero digits, so they're all considered significant or measured. Each digit occupies a separate place, so we count the number of places in that measurement. There's actually 3 different digits, 1, 4, and 5. All 3 of them are considered significant. So we say we have 3 significant figures. In the second number, we start with the 1, in this case in the thousands place. It's the farthest one, non-zero to the left. Notice that we do have a 0 immediately following it, but that 0 is considered captured between two non-zero numbers. It's right between a 1 and a 4. As a result, it is considered significant, and we count it so that we can continue counting the non-zero digits that follow it. In this case, there are 5 different digits: 1, 0, 4, 5, and 6. So we have 5 significant figures. Now the third example, our first non-zero digit actually occurs well past the decimal. We ignore the zeros at the beginning. This is the easiest way to remember that those leading zeros never count as significant. Start with the first non-zero digit on the left and count what follows. So in this case, starting with that 1, we have 5 digits total: 1, 0, 4, 5, and 6. And this number has 5 significant figures. It's the zeros at the end of a number that are the trickiest to determine. So in the fourth measurement, 1045.60 milliliters, the 0 at the end of the number does count. And this is because there's a decimal that is explicitly written in that number. I can see that decimal point. And that implies that any zeros that are at the end of the number must have been measured or estimated, but that's still considered part of the measurement. So in this case, we count all of the different digits: 1, 0, 4, 5, 6, and 0, and we say that we have 6 significant figures. Last but not least, if there is no decimal explicitly written into the number and there's a 0 at the end of it, it's really unclear whether or not that 0 at the end should be considered measured or just a placeholder. The safest thing to do is to assume that it's a placeholder and count only the digits that come before zeros at the end. So in this case, that would be the 1, 0, 4, 5, and 6 that start the number, and I would say that I have 5 significant figures. Now that we know how to determine the number of significant digits in any measurement, let's look at our multiplication and division rule. We're going to do a calculation of density here by dividing a mass of 51.842 grams by a volume of 2.7 milliliters. Now we plug this into our calculator and we get this number. Your calculator may actually show you a lot more digits than I've shown here. Obviously, this is too many places, way too many digits compared to the measurements that went into them. The operation that we did in the calculation was division, so that means we deal with rule number 2. Our answer can't have more significant figures than any of the original numbers. So we count the number of significant figures in each of our original measurements. And in the mass, 51.842 grams, we have 5 significant figures. In the volume, 2.7, there are 2 significant figures. So again, it's just the number of places that actually have significant digits, non-zeros, and zeros that are considered significant or measured. So we have to round our answer to have the same as the least number of significant figures. So that's 2 significant figures. That means that in our final answer, we start with the first non-zero on the left, and we count over till we have 2 significant figures. So that means that we're going to keep 1 and 9. Those are our 2 significant figures, and we're going to round away the rest of the number. We're going to use our rounding rules again. If we look at the 10th place, we have a 2 in that place. That's less than 5, so that means that we keep the number as 19. We round down to 19 grams per milliliter. We can apply the same rule to the volume that we calculated for our textbook. This is all multiplication in our calculation. So we have to look at the number of significant figures in the measurements that went into that calculation. So our first measurement is 30.10 centimeters. All of the zeros and the non-zeros, of course, count as significant in this number because there is a decimal explicitly written there. So we have 4 places written out, 4 significant figures. 24.35 centimeters is also 4 significant figures, all non-zero digits there, each one of them counts. And the same thing applies for 3.85 centimeters, except this time we only have 3 places represented, so 3 significant figures. This means that we have to round our answer to the least number of significant figures in our measurement, which is 3 significant figures. So we start with the first non-zero on the left in our calculated result, and we count over 3 places. And that takes us to 282. So there we go, 282 centimeters cubed. Now hopefully right now you're saying, wait a second. You can't round 2,821 down to 282. That just doesn't make sense. And you're right, it doesn't make sense. You can't necessarily just eliminate the digits you round away when they are on the left-hand side of a decimal place. Instead, if you have to round away a digit, you have to replace it with a placeholder 0. So it's more appropriate to round down 2,821 to 2,820 centimeters cubed. That placeholder 0 is problematic, so a better way of representing this number is actually to use scientific notation. 2.82 times 10 to the third centimeters cubed is exactly the same as 2,820. The advantage here is that we know that all of those digits on the left-hand side, the left-hand part of that number, are considered significant. Whenever you use the exponent to represent powers of 10, it's a placeholder. It's just telling you the overall magnitude. Those are never considered significant in the exponent. So this number, 2.82 times 10 to the third centimeters cubed, is the best way for representing the result of this calculation with the appropriate number of significant figures. Here are a couple of additional tips for dealing with significant figures in calculations. First, if you're dealing with a multi-step calculation, do all of the calculations for each step and get one final answer before you try to round to an appropriate number of significant figures. So you'll only round your final answer. You should look back at each step and figure out how many significant digits should have been kept and use that as a guide to figure out where to round your final answer to. But if you start rounding at each step, you actually introduce error, and you would find that the answer that you got could be significantly different than what it would have been if you hadn't rounded along the way. So the rule of thumb is round at the end. Second, assume that conversion factors that you use in dimensional analysis calculations are exact numbers. So this means that when you do a unit conversion, you don't have to count the significant figures for those conversion factors, those equivalent statements. The only ones that you need to count significant figures for are the actual measurements. So look at your starting measurement, count the number of significant digits there, and round your final answer to the same number of significant digits as in that first starting measurement. So in summary, the number of digits or significant figures in a measurement indicates the uncertainty of the measurement process associated. And it's important to report the measurements that you make with the appropriate number of decimal places or significant figures. It's also important to report the results that you calculate using those measurements with the appropriate number of significant figures. So that means you have to make sure you round your calculated results using the appropriate rule for the operations involved.